Welcome to Physics Hub. So we have already uploaded 2 videos on short notes, and the sections which were covered in those videos are solid state physics and analog electronics. You may watch them, the link is given in the description. Now today we are going to cover another section, digital electronics. So without wasting much time, let's start. So it starts with op-amp, characteristics of an ideal op-amp. Before going to that, let's look at the configuration of an op-amp. So 1, 2, 3, 4, 5, 6, 7, 8. 8 pins are there and they have their names. You can see it. Mainly used pins are pin 2 inverting input, pin 3 non-inverting input, and these 4 and 7 where voltages are applied, and 6 input output pin 6, and this pin 8 is provided to make symmetry. That's why it is called no connection. It is employed just to make symmetry. Characteristics of an ideal op-amp: open loop voltage gain is infinite, input impedance is infinite, output impedance is 0, CMRR common mode rejection ratio is infinite, slew rate is infinite so that output voltage changes simultaneously with input voltage changes. Output voltage V0 of an ideal op-amp is given by V0 equals to AD into V1 minus V2, where AD is the gain for the differential signal. V1 minus V2 is the difference in signal. But if V1 equals to V2, then V0 equals to 0. So in practice, V0 also depends upon the average level. Vc equals to V1 plus V2 by 2, and this is called the common mode signal. Therefore, the total output voltage is in practical V0 equals to AdVd plus AcVc, where AC is the voltage gain for common mode signal. CMRR is given by AD by AC, but the higher value of this CMRR gives you better performance. But for large value, CMRR is often expressed in decibel, and it is written as 20 log AD by AC with base 10. Op-amp is an emitter coupled differential amplifier. You can see the configuration, and this circuit amplifies the difference of the two input signal and acts as a differential amplifier. These are the two transistors which are employed to make this differential amplifier. Now what is input offset voltage? The voltage which should be applied between the input terminals to balance the amplifier is called the input offset voltage. Output offset voltage, the voltage that appears at the output with the two input terminals grounded, is called the output offset voltage. The input offset current, the input offset current is the difference between the two bias currents entering into the input terminals of the balanced amplifier. The input bias current is defined as the average of two separate currents entering the input terminals of a balanced amplifier. Now what is slew rate? I have already mentioned about this slew rate. Now what is slew rate? The rate of change of output voltage caused by a step change on the input, and which is measured in volt per microsecond or volt per millisecond. Slew rate, the formula for slew rate equals to 2 pi f into V, where f is the highest input signal frequency and V is the maximum peak voltage of the signal. If op-amp is required to amplify a signal with a peak amplitude of 5 volts at a frequency 25 kHz, then the op-amp with a slew rate of at least this equal to 0.785 volt per microsecond would be required. Slew rate 10 volt per microsecond means when a large step change is placed on the input, the device would be able to provide an output of 10 volt change in 1 microsecond. Now some of the configurations made of op-amp. So this is the inverting amplifier, where two resistances are used, R1 R2 with a voltage source Vs, and V0 by Vs, which is called the open loop gain, equals to it's called closed loop gain, minus R2 by R1. Non-inverting amplifier, this is the formula of again V0 by V0 by Vs equals to 1 plus R2 by R1. This R2 is called feedback resistor. Phase shifter, assume R1 and R2 are replaced by impedance Z1 and Z2. Then V0 by Vs equals to minus Z2 by Z1 and considering phase we can write them after the modulus value of these things, and using the exponential function we can write the phase. Thus the op-amp can shift the phase of the input voltage Vs by the angle pi plus phi 2 minus phi 1, which can have any value between 0 to 2 pi. Unity gain buffer or isolation amplifier. Look, the inverting input terminal, the output terminal 2 and 6 pin is shorted, and it acts as unity gain amplifier. Adder or summing amplifier, I current through this non-inverting input is given by the sum of currents I1 plus I2 plus I3 plus dot dot dot. Then this is equals to 0 minus V0 by Rf. Here we have used Ohm's law, and therefore V0 equals to minus Rf by R1 into V1 plus Rf by R2 into V2 plus Rf by R3 into V3 plus dot 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 plus Rf by Rn into Vn. If R1 equals to R2 equals to R3, and if these resistances are all equal, and then V0 is written as minus Rf by R1 into V1 plus V2 plus V3 dot 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 Vn, where the resistances have equal value of R1. This is differential amplifier, which amplify the differences of the provided signals. So this is the formula equals V0 equals to minus R2 by R1 into V2 minus V1. Integrated circuit, remember for integrated circuit the capacitance will lie parallel here as feedback impedance. So I equals to Vs, is Vs minus 0 by R equals to 0 minus V0 by this impedance, and this is equals to current I equals to dq by dt, and q equals to Cv, C into voltage difference 0 minus V0, and we got the output formula for output voltage V0 equals to minus 1 by RC integration over Vs dt plus this constant. So this is the ideal circuit for an integrator, and in case of practical one we need to add something. We need to add a parallel resistance R2 and a resistance here at the non-inverting terminal, and the values are decided. R1, this value should be equals to R parallel R2, and R2 should be such that it is much greater than 1 by omega C, and this resistance R1 is added to minimize the error due to offset, and this resistance R2 is added to avoid the problem of DC stability. This is the circuit of differentiator. So here the capacitor is connected here at the inverting terminal, and I equals to dq dt equals to ddt of C into Vs minus 0 equals 0 minus V0 by R. Therefore V0 equal to minus RC dVs upon dt. This is the basic circuit, but in practical we see some modification. The some resistances R1 and this resistance R is employed. The resistance R1 is approximately R by 10 or R by 100. This resistance R1 limits the high frequency gain and makes the practical differentiator useful only for frequencies well below the limiting frequency, which is given by 1 by twice pi C into R1. And this is the practical differentiator circuit. Logarithmic amplifier, I equals to I naught into exponential E into Vf by eta kBt minus 1. Here in the feedback portion we employed a diode, and it converts into logarithmic amplifier. If exponential EVF by eta kt is much greater than 1, therefore I equals to I naught exponential EVF by eta kt. We neglect this one term, one factor, and we got Vf equals to eta kt by E into ln I by I naught. Now applying KVL in this loop, we got minus Vf minus V0 equals to 0 in this loop. Therefore V naught equals to V0 equals to minus Vf equals to minus eta kt by E ln I by I0, that is equals to minus eta kt by E ln V1 by I0 into R1. Square wave generator or astable multivibrator. So a capacitor is connected in the inverting amplifier and a feedback resistor R is connected, and this configuration of R1 or R2 provide positive feedback. Okay, and this feedback factor beta equals to R1 divided by R2 plus R1, and this is the output plus Vsat minus Vsat. This is a square waveform, and this is the output at the capacitor, and the time period of the output waveform, this is basically a multi-vibrator, so it will have some frequency and a time period as well, and the time period equals twice into R into C into ln into 1 plus beta by 1 minus beta, where beta is given by this factor. And if you write them in terms of these resistances, then we got T equals to twice RC ln 1 plus twice R1 by R2. So very often you are given this type of circuit, and you just need to apply this formula to find out the time period. Once you know time period, you can easily find out the frequency by the formula T equals to 1 by F, where F is the frequency. Now, Schmitt trigger and regenerative comparator. We can also design Schmitt trigger using op-amp. So Schmitt trigger can remain in one of its two stable states indefinitely. It changes state only when a triggering signal is applied. For this here circuit is also known as bistable multivibrator. So this is the input voltage, and this is the non-inverting terminal, and voltage V1 is appearing here, and some reference voltage VR is given, and the same configuration is kept here of R1 or R2, and this is the output. So when V input is less than V1, V0 will be plus Vsat, and accordingly V1 will be given by this. Now what we are doing, we are just trying to calculate the output voltage, and that's why we are using superposition principle. So using superposition principle, we can find out the output voltage. Now this figure A shows transfer characteristics for increasing Vi, and B for decreasing Vi, and this is C is the complete transfer characteristics showing hysteresis. Triangular wave generator. So to do that, what we are doing, we are just adding a non-inverting Schmitt trigger whose output is a square wave, then an op-amp integrator which converts the square wave into a triangular wave. So first we are producing a square wave, then we are integrating it, which is producing a triangular wave. And these are some calculation, you can check it out. And if you are asked to find out the time period T1 equals to T2 equals to T by 2 equals to 1 by 2F equal to twice R1 RC by R2. Therefore the frequency will be R2 by 4 R1 RC. Feedback amplifier. So in case of feedback amplifier, we see with the basic amplifier a feedback network is added. So input signal is given through this, and feedback network is connected here, and some portion of the output is fed back to the basic amplifier. Therefore the net input voltage becomes Vs plus beta into V of A equals to open loop gain, and beta equals to feedback ratio. Output with feedback B0F. B0 means V output, and F represents feedback. This is equals to A into Vi equals to A into Vs plus beta V off. Overall gain AF equals to V0F by Vs. This is for positive feedback, A by 1 minus A beta. A beta is called loop gain, and AF is called closed loop gain. Negative sign will appear here for positive feedback, and positive sign will appear here for negative feedback. For positive feedback, we get AF equals to A by 1 minus A beta. If AF goes to infinity, as A beta goes to 1. This means that there is an output without any input. Actually the amplifier then turns into an oscillator. This is the BARC criteria. A beta equals to 1. The sample signal that is feedback may be derived either from the output voltage across the load or from the current in the load. If the feedback signal is proportional to the output voltage, then it is termed as voltage feedback. If the feedback signal is proportional to the output current, then it is termed current feedback. Thus, we have 4 basic feedback arrangements, and those are shown in this figure. This is voltage series feedback, this is voltage shunt feedback, this is current series feedback, this is current shunt feedback. You can check those configuration. And this inverting amplifier is an example of voltage shunt feedback. Remember that. Effect of negative feedback. So basically negative feedback makes the output less. So why should we use negative feedback? So these are some advantages of negative feedback. Firstly, it stabilizes the gain of an amplifier against circuit parameters and voltage supply variations. It reduces nonlinear phase and frequency distortions. It reduces internal noise in an amplifier. It increases the bandwidth and thus improves the frequency response of an amplifier. AVH means high frequency gain equals to AVM mid frequency gain by 1 plus J into F by F2. And in this graph you can see the gain versus frequency. So this is without feedback and this is with feedback. And look, although there is some change, but the gain bandwidth product remains constant. So AVHF equals to AVH by AVH into beta equals to AVM by 1 plus AVM into beta plus J into F by F2. Therefore, AVH equals to AVM by 1 plus J into F by F2 prime, where AVM is given by this, and F2 prime equals to F2 into 1 plus AVM into beta. Similarly, we can find out this F1 prime. So what is the change in frequency equals to F1 divided by 1 plus AVM plus beta. So this is basically greater than 1, so F1 should be shifted left towards left. But the gain bandwidth product is same. So all the negative feedback reduces the gain and increases the bandwidth. The gain bandwidth product remains constant. Now let's talk about oscillators. So firstly, BARC criteria for oscillation, and the criteria is A into beta equals to 1, and the overall phase shift around the loop is 0 or an integral multiple of 2 pi. RC phase shift oscillator. The op-amp used in inverting mode introduces 180-degree phase difference, and this is the inverting op-amp, and these 3 RC section introduces additional 180-degree phase shift at a particular frequency. So the total phase shift is 360 or 0 degree. And for this oscillator, frequency of oscillation F equals to 1 by twice pi RC into root 6, and at this frequency of oscillation the feedback ratio beta equals to Vi by V0 equals to 1 by 29. Wine bridge oscillator, this is the wine bridge oscillator CRRC R1 or 2 by voltage divider. Once RC series and later RC parallel with V0 and positive terminal. So this I have written to remember. And this is basically a audio frequency signal generator. The frequency of oscillation is given by F equals to 1 by twice phi RC. Tuned collector oscillator. It's a LC resonant circuit in series with collector of a transistor. The frequency of oscillation is F equals to 1 by twice pi root over LC. And this is Hartley oscillator. You just try to remember the configuration. Sometimes they give you the configuration and ask you to find out the frequency. Then you have just to find out, you have just to put the quantities in the expression of frequency and you will get the answer. So RFC is radio frequency choke, prevents current from reaching the collector supply. It also provides DC load to the collector. The frequency of oscillation is 1 by 2 pi root over L1 plus L2 plus 2m into C, where HF is greater than N1 plus L1 plus m by L2 plus m, condition for sustained oscillation. And this is RF radio frequency signal generator. Let's talk about Colpit oscillator. This is Colpit oscillator. The difference is here all L1, L2 was there, the inductor was there, but here same thing, capacitor, this will be replaced by capacitor C1, C2 and L will be here replacing C. So this produces RF radio frequency up to 1 megahertz, HF is gain. HF is greater or equals to C2 by Cn is the condition for sustained oscillation, and the frequency of oscillation 1 by 2 pi root over L into Cs, where 1 by Cs equals to 1 by C1 plus 1 by C2. Filters. Transfer function H omega equals to V0 by Vn. H is a complex function of omega, unlike the gains of resistive circuits which are real and constant. So this is first order filters using R and C, and the cutoff frequency omega is equal to 1 by RC, omega is equals to R by L. Transfer function H omega equals to 1 by 1 plus J into omega by omega C. Omega C is the cutoff frequency. This is low pass filter, and this is for high pass filter, just interchanging. And the formula for transfer function H omega is to 1 by 1 minus J into omega C by omega. This if you are asked to design second order filters, then some additional things are added here. RC was there, but here additional L is employed to make a low pass filter of second order. Similarly, the we can design the high pass filter by making some modification here, and accordingly the transfer function changes. So these are the transfer function for this is for low pass filter and this is for high pass filter. Now let's talk about band reject or band stop filter. Means it stops by a particular band of frequency. So it's basically a notch filter, and this is a simple construction or design using resistance, inductor, capacitance, and the transfer function is given by this. You don't need to remember these things still. If you require any day, then you can use it. So it can be constructed by combining a low pass filter with a high pass filter in parallel. So in this way we can design band reject or band stop filter. But remember that this omega h must be greater than omega L, and resonant frequency omega 0 equals to 1 by root over LC. Now band pass filter, similarly we can design it with R, L and C, and the transfer function is given by this, and we can design this band pass filter by making a series connection of a high pass filter and low pass filter. And remember one thing, that omega h must be less than omega L, and this is band pass filter. Resonant frequency omega 0 equals to 1 by root over LC. Band pass filter of a filter bandwidth of a band pass filter bandwidth equals to FC2 by minus FC1, and center frequency of a band pass filter if F0 equals root over FC1 into FC2. The quality factor FQ equals to F0 by bandwidth. Now Boolean algebra, octal number system 0 to 7, and this is the way to convert in decimal number to octal number, and if you have a decimal number, then this is the way to convert it into octal number. So this is so easy, so I'm not explaining it, I'm explaining this little much. So if you have some decimal, point decimal 0.22 into 8, then 1.76, so you just keep the integral part here and the carry here and the remaining part here, then multiply that remaining part with 8 again and take the integer part, and in this way we can convert the decimal into octal. Okay, so when these were integers, then we are going in this way, but when you are dealing with point numbers, we are going in this way. Remember that. Now the very easy, the easier way to convert octal number to binary, or sorry, into decimal, is to write the octal number into binary. Then you can easily convert them into, sorry, if you have any decimal number, then it is very easy to convert them into binary. So how can we do that? Suppose it's 365, then you just write 3 in terms of binary, and 6 in binary, 5 in binary, then you just write them side by side, then you will get the equivalent binary number. And once you know the binary number, you can easily go to the decimal number. Now hexadecimal number system 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 15. And in hexadecimal the numbers are transformed accordingly, 0, 1, 2, 3, 4 up to 9. Then for 10 we write A, for 11 B, 12 C, 13 D, 14 E, then for 15 we write F. And these are the binary equivalent 0, 0, 0, 0. The similar way, 15 we write 1, 1, 1, 1. And this is basically the same thing which we did in binary to decimal conversion. So this is a hexadecimal to decimal. So 1 into 16 to the power 2. If it were decimal, then you would have written 10 to the power 2 plus a means 10, so 10 into 16 to the power 1, and 7 into 16 to the power 0, then 2 into 16 to the power minus 1 plus 15 into 16 to the minus 2, because f is 15. De Morgan's theorem, a plus b plus c dot 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 complement equal to a complement dot b complement dot c complement dot dot dot. A into b into c into d dot 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 complement equal to a complement plus b complement plus c complement. This is the mathematical form of De Morgan's theorem. This is OR gate, AND gate, NOT gate. Y equals to a plus b, y equal to a dot b, y equals to a complement. These are the truth table. These are basic. These are very basic things. I'm not explaining, skipping it. NAND gate, y equals to a b complement. NOR gate, a plus b complement, a dot b dot. Just check the truth table. XOR gate, this is called inequality detector. The output is given by a plus encircled b, a b complement plus a complement b. Inequality detector means whenever the inputs are unequal, then only you will get high output voltage. XNOR gate, this is basically a combination of OR gate and NOR gate, and it is called equality detector, and the output given y equal to dot encircled b, ab plus a complement b complement. A dot b equals to a complement b complement whole complement. Equality detector means when the inputs are equal, then only you will get high output. 0 0 equal, 1 1 equal, so you are getting high. So 0 1 unequal, 1 0 unequal, so you are getting low output. Okay, so this one I have tried to prove. And note one thing, that a dot encircled b dot encircled c equals to a plus encircled b plus encircled c. Counter map. It's a very interesting and important thing. So first, let's know about min term and max term. Min terms, we get sum of product, SOP, and this is product of sum. Sum of products means, look, these are the product and we are taking the sum, and these are min term, M1, M3, M5, M7. 0 0 1 means 1, 0 1 1. So when we are talking about SOP, we take the complemented thing to be 0 and uncomplemented things to be 1. Then you get min term 1 3 5 7. So these are all uncomplemented, so 1 1 1, so 7. But for here, you see, the thing is just reversed. Complemented things are taken to be 1, and uncomplimented things is taken to be 0. So 1 0 1 means 5. So 1 to 5. Okay, so I have written explicitly here. So for when using corner map, we have to build up few tables, few types of tables. So this is one type of table. So when you only have two variables a and b, then we write a complement a, b complement b, and in this way there it is 0 2 1 3. Okay. Now how to remember this numbers? So when you have three variables a, b, and c, we write this a complement, b complement, then a complement b, a b complement, and this is c complement c. Okay, so 0 0 0 means 0. Here 0 1 0 means 2. 1 1 1 means 7. 1 0 1 5. In this way we just write the numbers, these numbers. And for if you have four variables, then it is written like this. Remember this thing, you just remember a complement, b complement, then a complement b, a b, then a b complement. Similarly, c complement, d complement, c complement, d, c d, c d complement. Here I have given you some example and how to reduce them. So when 2 at a time is selected, it's called pair. When 4 at a time is selected, it's called quad, and 8 at a time is selected, is called octet. So we have to try to cover maximum things. So look, here we can cover 4 1. So it's a quad. This 4 1 quad. This is a quad. But this is a pair. This is a pair, and this is also a pair. And accordingly we get this one. Now flip flop. So simple clock plus pulse time, this TP pulse width must be less than much less than the time period. Pulse width, the interval between two pulses, is called a period. SR flip-flop, clocked SR flip-flop. This is the configuration. Clock frequency is given 1 by T. 0 SR 00 last value given, 101 01 0 reset, 11 not allowed. So we need some other flip-flop to avoid this discrepancy. So we define JK flip-flop by using preset clear clock, and this is the truth table. So JK, when 00 it gives the last value, 101 010 reset, 11 given complement is complemented. So last it was not allowed, but it is now complemented. So when J is high, you get a high output set. To avoid uncertainty in the initial state of a flip-flop, preset and clear are used. If the initial state is made Q equals to 0, it is called clear, and if Q is made equals to 1, then it is called preset or set. If you put clear equals to 0, preset equal to 1, then Q equals to 0, that it reset the flip-flop. Clear equals to 1, PR equals to 0, then Q equals to 1, it means it sets the flip-flop. Clear equals to 1, preset equal to 1, the circuit operates in normal fashion, and when clear equals to 0, preset equal to 0 must not be used, since it leads to an uncertain state. Now there is the most important master-slave JK flip-flop. In a clocked JK flip-flop, there is a restriction on the width TP of clock pulse. It must be smaller than the propagation delay delta T. However, in IC form flip-flop, delta T is very small, and the above condition is not satisfied because of feedback connection from output to input in JK flip-flops. The input and output change many times during a pulse time TP. At the end of clock pulse, the output becomes ambiguous. This situation is called the race around condition. This difficulty is overcome by using the master-slave JK flip-flop. So this part is called a master, and this part is called a slave. It's a cascade of two SR flip-flops with feedback from the output of the second, called the slave, to the input of the first, called the master. Positive clock pulses are applied to the first flip-flop, and these are inverted before being applied to the second flip-flop. When clock equals to 1, the master is enabled. This is the master part. And when clock is 0, means this becomes 1, then slave is enabled. Since CK equals to 1, the master is enabled, and it follows the truth table of JK flip-flop. When the complemented thing is 0, the slave SR flip-flop is disabled, so that the information on the master's output is stored in the input of the slave. It is brought to the output of the slave only when clock goes low. In summary, the master responds like a JK flip-flop as the clock goes high, while the slave is disabled. During the clock pulse, Q does not change. But as the clock goes low, the information with the master is transferred to the slave. Thus, the race around problem does not rise. This is D-type flip-flop, and the truth table is given by this. In some synchronous digital system, it is often necessary to delay a signal by exactly one cycle of the clock. The flip-flop used for this purpose is called a delay flip-flop. Toggle flip-flop or T flip-flop. In a JK flip-flop, if J equals to K the resulting flip-flop is called a T toggle flip-flop. This is the output. This is a truth table. A flip-flop which responds only to rising edge is referred to as a positive edge triggered, and a flip-flop which responds to only to the falling edge is referred to as negative edge triggered. Sorry, E is missing here. For negative edge triggered flip-flop, a bubble is used at the clock input, but no bubble is used for positive edge triggered flip-flops. The register is a basic logic circuit which is used to store or shift the digital information. Here in the short note, I have shown some problem. Excuse me for that, but this is a very good problem. You can check it out. To store an n-bit word, now n number of flip-flops are required in a register. Entering the binary data into a shift register is called the loading, and shifting them or reading out them is called the retrieving. The process of shifting the data is performed with the help of clock pulses that are applied to the register circuit. Binary data can be entered into a shift register in two ways, in serial form or in parallel form. The same is true in case of retrieval. According to the register can be classified to operate in the following four modes: SISO, PISO, SIPO, PIPO. Serial in, serial out, and in the same way parallel in, parallel out, serial in, parallel out, parallel in, serial out. So this is the configuration of SISO, serial in, serial out. So data is entered serially and data is taken out serially. So that's why serial in and serial out. Okay, this is 3-bit shift register SISO. And it is working in this way. SIPO, serial in, parallel out. So that the output data are collected once at a time, not or simultaneously, all at a time, not once at a time. So serially in but parallelly out. So many things I have written. I am holding it, you just read. The number of clock pulses required for entering the data is equal to the number of bits in the data. This is the most important line. Now let's talk about counter. Digital counter is a sequential circuit that counts the occurrence of clock pulses applied to it. There are two basic types of counters: ripple counter or asynchronous counters, and synchronous counter or parallel counters. An n flip-flop counter will act as a divide by 2 to the power n counter modulus, the number of unique states through which a counter can progress before returning to the initial state, is called the modulus of the counter. The number of flip-flops required to build a mod n or divide by n counter is the smallest value of n, for which 2 to the power n is greater than n. This is the type mod n, mod 9, mod 8, mod 10. So number of flip-flops is 2 to the power n must be greater than this n. So if you take 3 number of flip-flops, then 2 cube means 8, which is less than 9. So we have to use 4 flip-flops. Similarly for 8, 2 to the power 2 means 4, which is less than 8. So you have to use 2 to the power 3 means 8. Highest decimal count n-1, since for mod 9 8, mod 8 7, mod 10 9. Asynchronous counter mod 8 ripple counter. This is the configuration, this is the truth table. To avoid false operation of the counter, the clock period must be greater than the total propagation delay plus an additional stop interval Ts, which arises in the decoding of counter output. T is greater than equals to NTP plus Ts. Minimum clock period T minimum equals to NTP plus Ts. So the maximum clock frequency F max equals to 1 by T minimum equals to 1 by NTP plus N plus Ts, which is the upper limit to be used in a ripple counter of n flip-flops. Ripple counter with modulus n less than 2 to the power n. A counter with mod number n less than 2 to the power n can be designed from a mod 2 to the power n counter if the unwanted extra states beyond n are eliminated. This can be done by connecting an AND or NOR gate as a clearing gate in the mod 2 to the power n circuit. The number of inputs to the AND gate is decided by the number of flip-flops that go into high state at the count n. This number is the same as the number of ones present in the binary equivalent of n. So mod 9 basic counter, mod 2 to the power 4, number of flip-flops required 4. Binary count 1 0 0 1 9. So 2 1 is there, so number of inputs to AND gate is 2. Mod 13, number of 1 is 3, so 3 number of AND gates. So this is a question. Construct a mod 14 ripple counter using a clearing gate procedure. So in this we can do that. Up and down counter. The up counter can be converted into down counter simply by connecting the complementary output Q of each flip-flop to the clock input of the next stage flip-flop. Okay, so if you connect this, it will change. In a ring counter with n stages, there is one output for each n clock pulses, so it is a divide by n unit. If the serial output of a shift register is connected back to the serial input, then the bits will circulate around the register, shifting by one flip-flop at each clocking. In this counter, one and only one flip-flop is set, T equals to 1, at any time, and this set condition circulates around the circuit. Twisted ring or Johnson counter. The system is divided by 2n counter. This is twisted ring counter. Check the circuit. Synchronous counter or parallel counter. In asynchronous counters, each flip-flop is triggered by the previous flip-flops, and hence the delay time of the flip-flops are additive, and total setting time for the counter is approximately the sum of the delay times of all the flip-flops. The problem due to propagation delay can be largely reduced by using a synchronous counter in which all the flip-flops are driven by a common clock. Here all the flip-flops change state simultaneously. This is a 3-bit synchronous counter with serial carry. Now clippers. So this is the circuit for a clipper. Diode resistance. If this is the input, so it clips this negative portion. For this we have introduced a voltage V. Then it clipped this negative part, but it is producing an output which is less than V minimum because a voltage source has been used here. This was a series clipper, but this is parallel clipper. So this is the input and this is the output. You can see this part is clipped. So I have shown you some configuration, you can check it. Clamper. The clamping network is one that will clamp the signal to different DC level. So clamping means it will not cut, it will just clamp down to a different DC level. The magnitude of R and C must be chosen so such that the time constant tau equals to RC is large enough to ensure that the voltage across the capacitor does not discharge. During the interval, the diode is not conducting. Okay, so a capacitor will be there in series in case of clampers. Capacitor diode resistance, and you see it is clamped. For a clamping network, the total swing of the output is equal to the total swing of the input signal. In general, the following steps may be helpful when analyzing clamping networks. Start the analysis of clamping networks by considering that part of the input signal that will forward bias the diode. During the period, the diode is in the on state, assuming that the capacitor will charge up instantaneously to a voltage level determined by the network. Assume that during the period when the diode is in the off state, the capacitor will hold on its established voltage level. Keep in mind the general rule that the total swing of the total output must match the total swing of the input signal. Okay. So when you are confused about the output voltage, apply KVL. So in this circuit I have shown you how to apply KVL, and I have made a video on this KVL, KCL things, superposition principle, etc. So these are two other circuits for clamper. Okay, now let's talk about D by A and A by D converter. Digital analog converter, weighted two converters such type, weighted resistor DAC, 4 resistors, and the weightage are R1 equals to R by 2 to the power 1, R2 equals to R by 2 to the power 2, then R by 2 to the power 3, and R0 equals to R by 2 to the power 0, R by 2, R by 4, R by 8. The output is proportional to the numerical value of the binary A3, A2, A1, A0. This is a reference voltage, and in this way we calculate the output voltage. So remember the final expression, V0 equals to minus VR into RF by R, 2 to the power 3 A3 plus 2 to the power 2 A2 plus 2 to the power 1 A1 plus 2 to the power 0 A0. And in another way we can design DAC, DAC, digital analog converter, R2R ladder circuit, RF 2R, 2R, R2R, 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 and this is a simplified circuit, and the output is basically very similar to the output of this. So here it was minus VR into RF by R into this thing, and here also VR into RF by R. So a 1 by 48 term is multiplied with this. Okay, so this is the way So if you have any question in the examination on this analog to digital and digital to analog converter, then you will be given these circuits. You just need to remember this formula and to have to apply the formula. That's it, because otherwise it is little difficult to remember these things. I will not recommend you to remember these many things, but try to remember this, or at least before you enter into the examination hall, just look at these formulas and you can remember it. It's not so tough. DAC specification of parameters: percentage resolution equals to 100 by 2 to the power n minus 1 percentage. The voltage conversion for resolution V reference by 2 to the power n in minus 1. So very often get sets question from this thing. Now let's talk about ADC, analog to digital converter. An electronic integrated circuit which transforms a signal from analog to digital. Analog means continuous, to digital means discrete form. ADC provides a link between the analog world of transducer and the digital world of signal processing and data handling. Now 4 types of AYD converters are there: dual slope, flash AD, successive approximation AD, counter control AD. Dual slope means two op-amps will be there, 2 comparators will be there. Dual slope. So this is very complicated circuit, but you have to remember few key points to identify what type of converter is this. Dual slope, 2 op-amps will be there and an in-bit binary counter will be there. The counter counts from 0 0 0 0 0 to 1 1 1 1 when to the 1 n minus 1 clock pulse is applied. As the next clock pulse to the n at a time t equals to t1, the counter is reset to 0. And here I have written some clumsy things. You don't need to remember, just read it. Not so important for exam purpose. Flash AD or parallel comparator. In this ADC, analog to digital converter, you will get so many diodes, so many op-amps. 1 2 3 4 5 6 7. Analog input voltage, V reference, priority encoder. So this is very easy to remember. Flash AD, digital output. 2 to the power n minus 1 comparators are required for an n-bit converter. This is a 3-bit flash AD. So 3-bit means 2 to the power 3 minus 1 means 7. 7 comparators are required. Successive approximation AYD converter. For an n-bit converter, the number of clock pulses required would be n, and hence it is faster than the counter controlled AYD converter, which equals 2 to the power n pulses. So successive approximation registers plus a D by converter, analog input, digital output. Successive approximation AYD converter. Counter controlled AYD converter, binary counter, D by converter, comparator, analog input clock. This AYD converter is comparatively slow, since as many 2 to the power n minus 1 clock periods for n-bit converter may be required for conversion. So for ADC, not many questions are set. So one question I remember which came in one of the set exams, that a particular ADC, analog digital converter, was given and you were given which type of AYD converter is this. So if you can remember some key points about the converters, then you can easily identify what type of AYD converter is that. Okay, and this is the end.